Hopefully, the two previous examples in the previous video did not give us the false impression that life is easy when we use this quick and dirty method. And indeed, it may not be always so easy. So here's another matrix. We want to find the Jordan form for that matrix. As usual, we compute the characteristic polynomial, find its roots. Here's a unique root. And then let's apply the previous method, the fastest one. Pick a random vector. Okay. Now compute n times that vector, take y equal n times v. We get another vector. Now take another compute again, n times y. And then we give it a name. No, we don't even give it a name. We spare a letter from the alphabet because this is 0, so we stop. And now we want to move backwards. So we start from the same vector that we used to start, which is this v here. We want to solve the equation. That's the equation. That's basically the equation nx equal v. And we find it has no solutions. Okay? And so, because the echelon form has a pivot in the last column. And we try to pick a vector outside the span. Which span? So the span of y and v. So here the vectors we have already, y and v. How do we pick a vector outside the span, typically? Well, in this case, since we are looking at the whole space, we can use the methods we already know, but in principle, if I here, the identity here is actually just one way to write a basis. That's the basis we had to start with. And we want to pick an element of this basis and add it to v and y so that we now get still a linearly independent set, but larger with not only two elements. And so this is a more general method, which is we want to extend this linearly independent family here, this linearly independent collection of two vectors. We want to extend it to a basis, but by picking vectors from a prescribed basis, not just any vector. So we write this matrix. This will be a 3 by 5 matrix. We perform row reduction, and after row reduction, we see which columns will have pivot. This one will have a pivot. This is the first one. The second one will have a pivot because the first two ones are not linearly dependent. And now which is the next one to have a pivot? It will be this one here. So we're done. We got 3 vectors which are linearly independent. It will be v, y, and e1. So let's call e1 z. And just to be sure that we are doing things correctly here, we try to solve again the system, to solve the system for z. When we solve the system for z, we see it has no solutions. The system has no solutions. And now we want to move forward. So we want not just find the solutions, but also do this computation here. We plug z here, and we want to see what w we get. And we do get some w. Now we put w here, we multiply again, and we get 0. So we have a little problem, don't we? We got 4 vectors. This one, w, z, v, and y. We got 4 vectors. That's a 3-dimensional space that we are working on. We got 4 vectors. So our method failed. So the method may fail, and this justifies that we'll pay the price of learning a method which is guaranteed to work.